Okay, so we will continue. So you know that in the stage Ranguta method, you are supposed to solve the following system of nonlinear equations, right? So you can see that, right? Uh, so basically, this is what you want to solve. Or Tn. Z1, that is what we use, right? Right, so we are supposed to solve this system, right? So now you know that this is an nonlinear equation because you know you have a z1 and then you will have a z1 here, you have a z2 and then you will have a z2 here, right? So eventually this turned out to be a system of nonlinear equation, right? So one of them will be incorporated in the other equations as well, right? So it's like a system of equations which you learn in A level, right? So clearly all of them are dimension Sm, right? So that is what you have there, right? So then you can write this as this. You want to see a Z, capital F of Z, right? So that is, you are supposed to solve a system like this, right? So for appropriate coefficient matrix and for appropriate vectors, you can see that you have a system, right? So which you have to solve, right? So Z is equal to F of Z is something you have to solve, right? So now, so let me round Z1, Z2 up to ZS and F is again, you know, a matrix like this, right? So small f of Tn plus C1 H, comma f of Z is this, right? So uh, Yn plus H time J is equal to 1 to S A1J Zj all the way up to f of Tm plus C1H Ym plus H time J is equal to 1 to S As J Zj, right? So this is a, you can rewrite this as a system of equations, right? So which whose matrix notation is this, right? So now what we are going to do is we are going to talk about the conditions for solutions of this system, right? So this is basically will lead to the Lipschitz condition which we learn in the explicit formula, right? So we are going to derive similar kind of results for this as well, right? So that is how we are going to proceed, right? Now suppose right? So we define a matrix norm, a norm Z, right? So obviously each Zi has components uh, in M length component, right? Because you know it is basically yn is a vector, right? So then Zn is obviously a vector, and then eventually you have to have a norm. So you define a norm like this, right? So in that case, we will try to see this. Right, so capital F of U minus capital of V is basically this. Oh, sorry, minus F of V. Okay, so eventually, if you define a function capital F like that, then you find f of u minus f of v, which is basically, because the way you define the norm, this is going to be maximum of this minus maximum minus that, right? So then you try to apply the Lipschitz condition, right? Very similar to what we did there in the explicit formula. We are going to do the same thing here, right? So in this case, you know that this is basically less or equal to maximum of L, right? You apply the Lipschitz condition, right? So then you will have this yn minus yn cancelled out, so eventually you will have 8 summation of j is equal to 1 to s aij u minus v, or uj minus vj, right? So that is the Lipschitz condition, right? So you apply this Lipschitz condition for this formula to get that results. So that eventually turned out to be in this way, right? So that is basically less or equal to HL maximum of 1 less or equal to I less or equal to F. That's, you all know, right? Aij norm of uj minus, right? So you use a lot of properties here. First you use the triangle inequality in the norm, and then you use the constant multiple inside the norm, right? So you use those two so that you get summation. Sorry, I forgot the summation here, right? So in between, summation j is equal to 1 to s, right? So when you take the norm inside the summation, you will get 1 less or equal, and then again you take the absolute value outside, that you give equal, and then it is a positive number, so you don't have to worry about taking it outside, and L is ln h are constant, so you don't need to worry about taking it outside the maximum, because there is no I involved in that. So eventually you will get this less or equal to HL times this, right? So this you can set it up as follows, right? So this is basically HL. This term you studied in maybe in the third year function analysis or function analysis, or the other numerical, right? Or third year numerical, somewhere you must have seen this as a matrix norm, right? So it is called maximum row sum norm, right? So this one is the sum of each row, and you take the maximum, so it's maximum row sum norm. We denote by the infinity norm of the matrix A, right? So let me say this as the infinity norm of matrix A, and then you take the maximum of this, so that turned out to be the norm of u minus b, right? So where Aij, you name this matrix as A, the coefficient matrix as A. Right? So these are very usual notations which we commonly use. So you can see that this is equal to that, right? That means, right? So you now know capital F satisfies okay, capital H, capital F satisfies the Lipschitz condition with the Lipschitz constant HL times A of infinity, right? So if this one is less than 0, then the system has a unique solution, right? This is basically the second year fixed point theorem, right? So you see that if the function capital F, which is a part of the fixed point theorem or fixed point formula, right? So if the function capital F has is has satisfies Lipschitz condition with Lipschitz constant less than 1, then we say that the function has a fixed point, right? So a continuous function on a closed bounded interval. If satisfies Lipschitz constant, we call it contraction mapping, right? So that is a function with Lipschitz constant less than 1, right, has a unique fixed point. So here, if that Lipschitz constant is less than 1, then we can say that it satisfies it is a contraction mapping, so there is a unique fixed point. So that means the function f is equal to capital F of z has a unique solution, right? So if this has a unique solution, then you can always solve it by using fixed point iteration, right? Or we solve it by fixed point iteration. Okay, so we solve it by fixed point iteration. Now if you recall what we did in Euler method, right, implicit Euler method, right? So that also at the very beginning of this course, right? So in the implicit Euler method, we do the same thing, right? So we use the fixed point iteration or fixed point theorem to confirm the existence of a fixed point, right? That guarantees that the implicit Euler method has a solution at each step, and then based on that we apply some kind of a fixed point iteration to derive the solution at each step, right? So same thing goes here with the Ranguta method, but here because you have a more complicated function, you have a little more complicated Lipschitz concept, right? So that is the different here, but eventually it is same as what we did in Euler method. So this is how we can think of solving a Ranguta method, implicit Ranguta method, because we eventually has to apply the fixed point theorem at some point. So I'm going to stop here, and in the next class I will start talking about order and other concepts of a fixed point iteration, right? So we will continue the rest in the next class.